Hello everyone. My name is Conley Zhou. I'm from State Key Laboratory of Virtual Reality Technology and Systems, Beihang University. It's my great honor to present our work today. The title of our work is a video-based augmented reality system for human-in-the-loop muscle strength assessment of juvenile dermatomyositis. First, I would like to give some background information. Juvenile dermatomyositis, as known as JDM, is characterized by skin rashes and muscle weakness. This work mainly focuses on muscle strength assessment. As can be seen in the video, the child with JDM staggers when climbing the stairs, where another healthy child climbs the stairs with great ease. Juvenile JDM has an acute onset and is difficult to treat. There are approximately 2 to 4 children per million affected by JDM. However, the lack of pediatric specialists results in missed assessment and missed access inevitable. For example, in 2014, there were only 0.43 per pediatric specialist per 1,000 children in China, which was significantly lower than that of 1.46 in the US. Therefore, it is necessary to develop a decision-making system for a reliable and timely economical diagnosis for GDM. On the one hand, human diagnosis is always restricted by personal biases. On the other hand, similar to any machine learning algorithm, the automatic action quality assessment, as known as AQA algorithm, cannot guarantee 100% accuracy, making them not suitable for biomedical applications. Furthermore, the use of AR technology we argue that the use of the AR technology has the potential to be used in GDM diagnosis. Next, I will dive into the main methodology. That can be, we propose a human-in-the-loop AQA framework for muscle strength assessment of GDM. As can be seen in the figure, a doctor is assessing the muscle strength of a child in the pre-assessment clinic. Our core insight is to use the virtual character to represent our AQA result and provide a machine score for clinical doctors such that they can effectively compare the difference of moments of the virtual character and the real world patient as a key for effective human verification. Our work contributes 3 parts: JDM dataset, AQA algorithm, effective AR verification system. We propose a new large-scale video action dataset. In total, it contains 13 types of actions. The details of this dataset is shown in this figure. We also construct a 3D animation dataset covering each skill level of all types of actions. Our AQA algorithm aims to automatically access the muscle strength of assessment for children with GDM. We have also found that the existing AQA algorithm has suffered from a negative transfer problem. That is to say, the model pre-trained on large-scale action recognition dataset may be suboptimal for the AQA algorithm. To address it, we have proposed a constructive regression module. Given an unobserved sample, our AQA algorithm outputs a predict score, which is to retrieve a corresponding animation from our 3D animation dataset. Thus, we can synthesize the augmented scenes for effective human verification. When there is a large difference between the virtual character and the real-world patient, thus it is easily for clinical doctor to detect the difference and re-evaluate carefully by reviewing the assessment criteria. We also explore the optimal way of augmenting the virtual character into the real-world scene. Firstly, we have performed free space division by using an object detection algorithm and solving a simple optimization problem. Second, we have used a semantic segmentation algorithm to determine the optimal position by establishing a local coordinate. The orientation of the real-world patient can be determined. We also render the key parts of the virtual character and the real-world patient for effective human verification. These attentions are learned from our network heat maps. This slide shows a demo of the AR effects rendering. And demo 2. Next, I will introduce some result cases of our system. As can be seen in the video, the little boy is sweet when he gets up from the ground, and subjectively judging the different levels is quite difficult. Unfortunately, our model output the mild difficulty grade 3 to the severe one grade 1. At this point, the clinical doctor can make a accurate assessment by observing the large difference between the virtual character and the real-world patient. More demos are shown in this slide. Next, I will show the user study and the results of our experiments. The user study aimed to explore whether the proposed system can assist non-specialists in assessing muscle strength more accurately for children with JDM. We need to investigate two questions. How fast and accurate are the participants when accessing a given sample? To this end, we have designed two tasks. Task 1, CMAS assessment, and task 2, assisted assessment. The assisted assessment is under the help of our system, where the CMAS assessment required participant only using the assessment criteria. We first performed a comparative study to evaluate the effectiveness of the attention effects. As shown in the figure, over 90% respondents include doctors, parents, etc. prefer highlight the key parts for effective verification. Thus, we can verify the attention effects and virtual character as a whole. On the one hand, we have implemented two other algorithms for muscle strength assessment. As can be seen, the result in the below slide. It demonstrates the effectiveness of our AQA algorithm. On the other hand, our AQA algorithm had achieved greater accuracy than a participant when performing task 1 by only using the assessment criteria, demonstrating that the effectiveness of our AQA algorithm. Finally, we also compare the average accuracy and the average time usage for participants when performing two tasks. The results show that our system can assist them in for muscle strength assessment in a more fast and accurate manner. Finally, I would like to conclude my presentation. Through side-by-side comparison, we aim to construct augmented scenes to assist clinical doctors in accessing muscle strength and monitoring the rehabilitation process of patients. However, to apply such a system into real-world scenes, several technical challenges would need to be further addressed, including developing robust computer vision algorithm, designing a user-friendly interface for clinicians to interact with the system, ensuring the system is accurate and reliable across a range of conditions, etc. Thanks for your listening.
Thank you. Do we have any questions here?
Thank you. Very cool presentation. I had two questions. The first one, I thought I had read somewhere on one of your last slides, like an assessment for like non-professionals. So I was wondering, why would a non-professional need to assess it? And also, is like a clinical doctor, wouldn't they know how a child that has this condition move anyways?
I think our system aims to assist non-specialists in the pre-assessment clinic because the pediatric specialist is rural and their time is valuable. So we suggest patients go to the pre-assessment clinic for pre-assessment.
Okay, cool. Okay, yes, that makes sense. Second question, how easily do you think it is to fool this system? Because I feel like children move very differently, and the animation is like it's a very like, I don't know, perfect standard, like getting up animation.
Yeah, we have to admit that our system is a prototype system that have many points need to be further addressed. This could be our future work. Thanks.